Okay, welcome back, and let's collect some more XP points towards our math practice. The skills required for this practice are to be able to recognize these type of equations as something times something equals 0, or something times something equals 0 in this format. Either way, the most important thing is to be able to recognize them. If you want more practice with this is exploring detail in the 8th episode of this series. All right, so this one right here is written as a refresher, so making sure that we don't forget to solve how to solve the type of equations that we practice on the 2nd and 5th video of this series. But if you need to pause and try them now, go ahead and do so. I do want to point out before we check these that the most important skill required for this practice is to be able to factor these type of expressions, which we explored in detail in the last video. So pause now if you want to try these two problems. And we're going to check them now. So remember that this one's very easy and nice and convenient because we read it as something times something equals 0. Either we have two options, either the first something is equal to 0 or this other something is equal to 0. What makes the first one equal to 0? When x is 7. Or what is our other alternative? When x is negative 12. All right, so hopefully you remember that we made each something equal to 0 and got a 0 in return. All right, the next one, again, is a different format, but it's still, if you need to write the parentheses, can be written as something times something equals 0. What value of x makes the first something equal to 0? Negative 4 can not ever change. It's always a negative 4. So only option is to multiply that by 0. Or the other one is when this something is equal to 0, that is when x is 9. Or the opposite of that, which is negative 9. There we go. We have two possible solutions for both of those. And recognize them as something times something. If you're more interested, the actual name of the properties is the zero product property, but you don't have to know the name of that property to be able to solve these. That's the good thing. All right, so like I said, this is a refresher, and I'm going to check this at the end of the video because it's not really the same concept as what we're going to do today, which is solved by using this main idea of factoring. We will check this at the end of the video, okay? All right, great. So like I said, the most important skill for this practice is to be able to factor these type of expressions where we usually have three terms. Not all the time, but most of the time we have three terms, where the first one is some form of k squared, and the second one has some constant or some integer times just k, not k to the second power, but just to the first power. And usually there's a constant or a integer by itself with no variable at the end, all right? So remember that idea is, these are specially written so that there's no greatest common factor, all right? If you are not familiar with the greatest common factor, we'll explore that in future practice. So what we said when that is the case, that this must have been something times something. Now we're doing the opposite of distributing, which is undistributed or factoring, all right? And the first one's very easy to target. What did we multiply to get x squared? It was an x times x term, all right? So we know that it's a something times something that's more advanced, or that has two terms. Those are called binomials, if you're really into that. And then we have to figure out one of the things that we explored very in detail in the last video is that this is called the product, or the two numbers multiplied in negative 48. And this integer is called the sum, or the two numbers add up to 8. Can we solve that puzzle? Is there two numbers that we can identify, a pair of two numbers that multiplies to negative 48 and combines to 8? It must be some form of, not 8 times 6 won't work because the sum does not make 8. So try other combinations, probably 12 and 4. 12 and 4 seems to work. If we need to get a positive 8, that means that it was x plus 12 and x minus 4. All right, so check that. The sum is 8 and the product is negative 48. So that one checks and it is factored. All right, we can use the same idea here. The product is negative 10. The sum is negative 3. In other words, the two numbers add up to negative 10 and the two numbers combine to negative 3. What can we think of? If we already went through that thought process of n times n, what's the two terms for n squared? Then those two numbers must be some form of 5 and 2, it looks like to me. Some form of 5 and 2. And that's only if we have a negative 5 and positive 2, because negative 5 plus 2 is this negative 3 here, and negative 5 times 2 is this product of 10, negative 10, I'm sorry. And last one, similar format. How do we get a k squared? By multiplying k times k terms, k squared. And product is 18. Two numbers multiplied to 18 that combine to a negative 9. What is that pair? It must be some form of 6 and 3. And if it's going to be a -9, those two numbers better be negative, because -6 minus 3 does combine to a -9, and -6 times -3 is a product of 18. There we go, those check. All right. And the main reason for doing that, like I said, our main goal for today would be to solve the type of equations that might look something like this. N squared minus 3n minus 10 equal to 0. One of our favorite numbers here. And same for this one. K squared minus 9k plus 18 equal to 0. If that was given to us, are we now able to solve this equation? And the answer is yes, like we did in the previous problem. Something times something equals 0. Either the first something is a 0, which that would be n equals 5, or the other solution would be n equals -2. And that's how we would solve that equation. With that skill alone, we can make these type of complex looking equations very easy to solve. If we recognize that we can undistribute this or factor it as something times something equals 0, then it's very easy to solve. What's the first value of k that makes the left something equal to 0? That would be when k equals 6. And what would make the other value of k that makes the other something equal to 0, or the other expression? That would be a 3. So look how quickly we would be able to solve these type of equations if we were able to factor them. All right. So if you don't believe, you can always check, plug in the 6 to this whole expression. Wherever there's a k, plug in a 6 and then plug in a 3, and you should turn out to get 0. And the easier way to check is to plug it into this one. All right, because remember, they're the same. So next, let's test that ability. I didn't do this one because we're going to do it right here. Notice how this expression here is the same as this expression on the left side of the equation. And because we already knew how to factor that from before, all we need to do is the last step, which is turn both of the somethings equal to 0. And what was the factored form? X times x for the x squared. I believe we said plus 12 and minus 4. If it was written the other way around, where x minus 4 times x plus 12 is on the right side, that's okay. The order doesn't matter when multiplying, as long as we list the two solutions with their appropriate symbols, okay? So what makes the first something equal to 0? It is when x equals -12. Or the other option is to have x equals, what makes the other expression equal to 0? When x equals 4. Those are our two possible solutions for that complex looking equation. Look at that. All right. Having the same type of thinking here. Even if the zero's on the left side, that's all right. That's not going to intimidate us. We're okay with that kind of thinking. But hopefully the main idea is to recognize it as something times something. All right. There's another way to solve these, but this will make our lives much easier if we're able to see that. What was multiplied to get this x squared? It was an x times x term. And now we have to identify the product and the sum. The two numbers multiply to a -21. And those same two numbers combine to a -4. What are the possibilities? There's many, but the only one that works here is going to be some form of a 7 and 3. And even that is not specific enough. Only if we have a -7 and +3. So again, this could have been written as x plus 3 times this x minus 7 in reverse order. So as long as it's written with the correct symbols, I'm going to write either x is a 7 or x is a -3. All right, those are the two solutions for this equation. And I wrote this one here on this format on purpose because this is not always going to be written in this format, where the last number is going to be a the product, and the middle number is not always going to represent the sum. So please look at the format so that if it's given to you like this, you don't make that mistake where you might think, oh, now the product is -7 and the sum is 12. That's not correct. Notice how these were in x squared, x to the second power. What is the power of this x? It is 1. Notice how it is descending, and technically this is times x to the 0 power. All right. If you don't know that, it's because you're not familiar with exponents. That's all right, but just recognize that this is technically the same. All right. If you haven't, that's because x to the 0 is a 1. So 21 times 1 is still a 1, but just make sure that you get used to it. If you need it, write it in that format, x squared minus 7x that we've recognized from before, plus 12. So that way we know, based on our previous thinking, that this represents the product and this one the sum. What are the two possible numbers that can multiply to a 12 and combine to a -7? That must be some form of 4 and 3. And only if we have -3 and -4. So now we turn it into the something times something equal to 0 form, which is very easy to solve. We're going to be doing a lot of those in the future. Gives us x equals 3 or x equals 4. Hopefully I gave you enough time to try those on your own if that's what you were trying to do. And either way, whether you did it before or after I did, that we got the same solutions, even if we wrote them in different order. All right, here are the types of examples that you may see regarding this idea of factoring. Again, hopefully you recognize, oh, this might be factorable when they are of this format. It could possibly be written as something times something, not all the time, but it's always worth checking. Can I factor this by finding the two numbers that multiply to a -72? And remember that this number implied that's not written as a 1. All right, so the sum is +1. The product is -72. What could that be? Some form of 8 and 9. And because this is +1, then it better be a n plus 9. N plus 9. And the other something is n minus 8. Check that. That should definitely work. And that way we know that one of the solutions is 8. And the other possible solution is n equals -9. Both of those will satisfy the equation, whether you plug it into the top version or the bottom version in green. Okay. There we go. Two possible solutions, and those worked out. And here, same idea. We know that this is always convenient to check. Can I write this as something times something? And it turns out this one for sure, absolutely. This is some form of 5 and 5 to make a product of 25 and a sum of -10, only if both of those are negative. And remember, we've asked before, is this a special type of problem? Because do you notice something about it that might make it special? And it is a perfect square, which means that, well, look, we would say either k equals 5 or k equals 5. Are those the same or different answers? They're the same. So that means that really there's only one answer. All right, there's only one answer. And why is that? I'll show you another way of solving it that hopefully, well, I'll remind you, not that I show you, because we should be familiar with it. All right, k equals 5 or k equals 5, not needed to be written twice, it's just k equals 5. But remember, what was it that made this special? Is that we can write it as something squared equals 0. And k minus 5 is a something. And the square root of 0, there's no positive and negative version of that. It's just k minus 5 better be equal to 0. So k equals 5. That's how we would solve. That's how we used to solve these type of equations before, with perfect squares, which is what we're not, hopefully we're not going to forget in the future. Look, is this what it says on the next part? We're going to remind ourselves to also think this way, not forget it at all. And maybe we can do two ways of solving this one as well. All right. But again, if we are in the form of thinking something times something, this one doesn't really fit that pattern. So I'm going to think about it as, here's what I'm going to do. I should have done that first. I'm going to rewrite this in a different way. I'm going to make it fit the pattern that we had before. It had to be something like 0 equals x squared, the x squared term. And notice how it's k squared, and then there's a k term. There's an n squared, and then there's an n term. So this one should have an x squared, and then there's an x term. But the original equation has no x term associated with it. So what number can we associate with being nothing there? It's a 0, so we can say plus 0k or minus 0k, however you prefer, and then minus 36. So that's one way of thinking about it. And I realize that's not a k term, that should be an x term. Let's fix that. All right, caught my mistake. And then we can think about it as 0x or minus 0x. And we think of two numbers that multiply to -36 combined to 0. What are those two numbers? Some form of 6 and 6. Now, is this one special? Not in the way that the last problem was special, because they're not the same. It's not a perfect square. But it's special in that the original problem only had two terms, and it was different from all the other ones, right? So it has that kind of specialty to it. And now we can say that x equals a positive or a -6. Right? So we can still solve these by factoring. And hopefully at the end, once you get really good at these, you may be able in the future eventually skip this step and go straight from here to here. But I'm just showing you one time, or maybe I'll show you a few times in the future so you can see the thinking for yourself. All right, remember that there's another way that we used to solve these before. So how do we approach these problems in the future? I'm going to say, or the other way of approaching them was x squared minus 36 was equal to 0, is that we recognize both of these are perfect squares, and what we have done before is add 36 to both sides. So we have x squared equals to 36, and then we know that something squared equals 36, there's two possibilities, positive or negative 6. So whether we wanted to add 36 to both sides and then take the perfect square, we got the same answer as we would have if we just did it by factoring from the first step. So that's pretty cool that in math you can do take two different approaches that are correctly mathematical thoughts, but arrive at the same answer in different ways, which is kind of cool. And like I said, if this is probably up to this point, this is the main factoring type of equations that you might see. So if you feel like you're a little bit rusty or shaky with your perfect squares, let's revisit them. Okay, so we're gonna solve these something square equations. This one don't have equal to 0, so I don't think factoring, but I do not recognize something squared. Something square equals 121 was the way we used to think about this. What two numbers can we square to get a 121? That's the key question, is that there are two numbers. One of them is positive, the other one is negative what? 11. And the something inside is still x minus 3. So the something better equal a positive 11 or a negative 11. And remember, this is just plain out simple algebra from here. We need to reverse the subtracting 3. We will say that x equals 3 plus or minus 11. So either x equals a 3 plus 11, which is 14, or x equals a 3 minus 11, which is negative 8. Those are our two solutions. 3 plus 11 is 14. 3 minus 11 is negative 8. That looks all right. If not, I'm sorry, but the concept is correct. I'm trying to go a little bit faster. All right, and one thing to always ask ourselves, was this one a perfect square? Yes, therefore we represent as a perfect square integer. Is this one a perfect square, the 82? No, but what two numbers can still be squared to get that? A positive or negative square root of that number. And the something is x plus 6. How do we reverse the plus 6? By subtracting 6. So be careful. I'm going to represent the solution as negative 6 plus or minus the square root of 82. All right, those two are a little much friendly looking. Even though this is not that much harder, it does look more intimidating. And that was the original problem from number 1. So let's solve it now. This is our last problem for this practice, and this is as a refresher. All right, let's see if you still got this. We have something squared equals to 81 over 16. And same kind of thinking, what two numbers were squared? I noticed those the numerator and denominator both have perfect square numbers. So square root of 81 over square root of 16 is going to be 9 over 4. Plus or minus 9 over 4 was squared to get 81 over 16. The something inside was x minus 3 over 4. And the last thing we need to do is reverse. This looks like subtracting that fraction. What's the opposite of subtracting that fraction? It would be adding that fraction to both sides. We will get a 3 over 4 plus or minus 9 over 4. And I guess I can write that as, so remember that it means 3 over 4 plus 9 over 4, which is a 3 plus 9 is 12, so 12 over 4. That can be reduced to a 3. Or the other option was to write it as 3 over 4 minus 9 over 4. And that one is the same. We're going to write that as negative 6 over 4 and then simplify them later. So I can write that as x equals 3 or x equals negative 3 over 2. All right, those are our two solutions. And two different methods that we use so far up to this point for solving quadratic equations. Quadratic equations involve equations where it has something squared in it. All right, so that's what we mean implied by quadratics. Equations involve something squared. All right, it could be whether it's a something squared or like the factoring problems we've been doing before. All right, so up to this point, the first type of problems we've been doing, I call them solving by perfect squares, because they either look like something squared equals some number, I'm gonna call it some constant k, or we have them of the form something squared equals some constant k, where the something is a little more advanced. All right, so x plus some c. I don't know. I'm using different variables, hopefully. All right, and the other one was by factoring. Just to summarizing the two methods that we use so far to solve equations. All right, by factoring, and usually it's in the form of 0 equals something times something. So x minus some other x, I'm gonna call it x sub 1, and x minus some second x value. And they can also look of the form something times something minus some x value. All right. That's the main idea. I mean, if this is a little difficult to remember or understand, just remember that the two main methods that we use are by taking perfect squares or using square roots, and the other one is by factoring. All right, that's the end of this practice. This is going to a really good place, and we're going to combine a lot of concepts soon. I'm looking forward to doing that again. All right, have a good day, and